Welcome to AI Peer Review. We're the show that dives deep into the latest research so you don't have to wade through it all yourself.
And today, we're looking at something pretty fundamental, a potential solution to what's arguably the biggest hurdle for the next wave of vision language models.
Yeah, the data problem, specifically the scaling problem. It's just immense, this need for supervised data.
It really is. We've gotten pretty good at making these models bigger, more complex, but training them, that still relies heavily on methods like supervised fine-tuning, RLHF, RLVR.
All of which need humans. Humans looking at images, writing descriptions, ranking outputs. It's slow. It's expensive.
Insanely expensive. Which brings us to this really interesting paper, Vision Zero, Scalable VLM Self-Improvement via Strategic Gamified Self-Play.
Vision Zero. I like the name. It sounds ambitious.
It is. Their whole goal basically is to figure out how to get VLMs to train themselves with zero human supervision involved in the loop after the initial setup.
Okay, so bypassing that whole data bottleneck entirely. That's the dream, isn't it?
Pretty much. Our mission today is to unpack how they actually did it, how they built this system where the models generate their own training data by, well, playing a game against each other.
Let's really underline why this is so critical, though. The cost figures are just staggering. The paper mentions the Kodo-CO attributes dataset.
Yeah, over $60,000 for annotating, 200,000 objects?
And Ego 4D. That was like 250,000 hours of human annotation work.
It's just not sustainable, right? Especially if we want these models to understand the complexity of the real world. You need vastly more data than that.
And it's not just the cost, is it? There's this other idea they bring up, the knowledge ceiling.
Right. If all the training signal comes from human labels or preferences, well, the model can only ever learn things that humans already know or can easily verify.
So it can't really surprise us. It can't develop strategies or insights beyond our own.
Exactly. You're kind of capping its potential from the start, which is why people have looked to self-play for a long time.
Like, in games. TD Gammon with backgammon way back when, or DeepMind's AlphaGo, AlphaZero.
Precisely. Those systems became superhuman because they learned by playing against themselves millions of times. They weren't limited by human examples. They discovered completely new strategies.
But, okay, Go and chess have very clear rules, discrete moves. How on earth do you set up a self-play game for something as messy as understanding images and generating language about them? It feels much harder.
It is much harder. And that's the cleverness of Vision Zero. They designed this specific, strategic, gamified environment. It's domain agnostic, meaning it doesn't rely on one type of data.
And it's based on who is the spy, like the party game.
Kind of, yeah. Inspired by it, it sets up this really neat dynamic. You have multiple players, all instances of the same VLM.
Okay.
Most are civilians. One is the spy. The key difference is what they see. Civilians get an original image. Let's call it IAC.
The ground truth.
Right. The spy gets a slightly modified version, ideas. Maybe an object is missing or added or changed somehow. Subtle, but important. Ah, okay, so there's an information imbalance right from the start.
Exactly, and the game unfolds in two stages. First is the clue stage. Every player, spy included, has to provide a verbal clue based on the image they see.
Ooh, interesting. So the civilians need to be accurate, describe what's really there, but the spy has to lie.
Well, strategically mislead, let's say. The spy knows their image is the odd one out, so they need to give a clue that sounds plausible, maybe focusing on things that are present in both images to try and blend in.
Well, the civilians have to be truthful, but maybe not too specific, otherwise they might accidentally reveal the difference.
Precisely. It forces this complex interplay. The civilians are pushed towards accurate visual description and clear language. The spy is pushed towards strategic deception and understanding commonalities.
Okay, that's the clue stage. What happens next?
Then comes the decision stage. Now, the civilians look at all the clues everyone provided, compare them against their own original image, and they have to vote. Who do they think the spy is? So that directly trains things like logical reasoning, spotting inconsistencies, comparing descriptions.
Deduction, discrepancy detection, yeah. All the good stuff. And notice, the only input needed is the pair of images, the original and the slightly modified one. No human labels about what's different, no text annotations needed.
Which makes generating the training data much easier.
Massively easier. And they really proved this works across different types of data. They tested it on 3 distinct domains.
Right, let's talk about that data. It shows the flexibility. First was synthetic data.
Yeah, they use SEAL VR, which is
Right.
common for visual reasoning, synthetic scenes with objects. They just programmatically changed colors or shapes of a couple of objects. generated thousands of these image pairs in like 6 GPU hours, super fast, fully automated.
Okay, that's the easy case. What about trickier stuff? Real-world images, charts.
Exactly. For charts, they used images from the Chart QA dataset. But editing charts accurately, like changing the height of one bar subtly, is actually really hard to automate with standard image tools.
So what did they do? They didn't manually edit thousands of charts, surely.
No, this is where it gets really clever. They used another large model, Gemini 2.5 Flash, not to label, but to create the modified image pairs.
Wait, they used an AI to generate the training data variations for the AI they were training?
Yep. They basically prompted Gemini, take this chart image, swap these specific numerical values, and re-render the chart accurately with those changes. It's like meta-automation.
That's brilliant. Solves a tricky engineering problem right there.
And then for general real-world images, they sampled pairs from the ImageEdit dataset, which already contains images with natural variations or edits. Again, just needed the pairs.
Okay, and the cost. This is the
Yeah.
kicker, right? Compared to that 60 grand for Coco.
They said generating the chart data and the real-world data cost them tens of dollars.
Tens of dollars.
Yeah.
That's not just cheaper. That's a different category entirely. It completely changes the economics.
It shifts VLM training from being potentially capital expenditure limited by human annotation costs to being almost purely compute limited. And the models are doing the teaching themselves.
Okay, but hold on. Self-play, as we said, it's powerful, but it can stall out, can't it?
Yeah.
If the players just reach an equilibrium where neither can beat the other with their current strategies.
That's the classic problem, yeah. Premature equilibrium or hitting a knowledge plateau, the game stops being challenging enough and learning grinds to a halt.
So just having the cool spy game isn't enough. You need a mechanism to keep the learning going.
Exactly. And that's the second key piece. The algorithm they call iterative self-play policy optimization, or iterative SPO. That's the secret sauce ensuring the models keep getting better.
Iterative SPO. Okay, let's break that down. How does it stop the system getting stuck?
It works by cleverly alternating the training focus between those two game stages we discussed, the clue stage and the decision stage. It's constantly balancing the training.
Right, so let's look at the clue stage optimization first. That's the part where they're generating descriptions. You said it's like a zero-sum game.
In that phase, yes. The spy wants to blend in. The civilians implicitly want to expose the spy, or at least not get wrongly accused themselves. The main reward signal comes from who gets voted for.
So if you get lots of votes saying you're the spy, you get a low reward. Simple enough.
Basically, yes. But there's a problem. The spy knows they have the different image. That's a huge advantage. Without correction, the spy might just learn very simple, generic clues and win too easily.
Making the game unbalanced.
Potentially, yeah. So they introduced something called role advantage estimation, RAE. It's a way to adjust the rewards to account for that built-in information asymmetry.
So it levels the playing field a bit. Make sure the civilians aren't unfairly penalized just because the spy has secret knowledge.
Exactly. It stabilizes the training, keeps the competition meaningful for both roles. It stops one side just dominating due to the setup.
Okay, that handles the clue stage. Then the system can switch focus to the decision stage. And that's more like standard reinforcement learning, right? Trying to make the correct prediction.
Yeah, RLVR reinforcement learning with verifiable rewards. The goal for the civilians here is simple. Correctly identify the actual spy based on the clues and their own image.
And the rewards here are interesting too, you mentioned. It's not just win or lose.
Right. They did something smart. You get a positive reward, say +1, if you correctly identify the spy. You get a significant penalty, say -1, if you accuse the wrong player.
Standard enough. But what's the clever bit?
The clever bit is the middle ground. If the civilian recognizes that the clues are too ambiguous or the visual difference is too subtle and it outputs nah, essentially saying, I'm too uncertain to guess, it gets a smaller penalty, maybe never on 0.5.
So it incentivizes calibrated confidence. Don't just guess wildly if you're unsure. Acknowledge the uncertainty.
Precisely. That's crucial for building models that don't just hallucinate answers when they're out of their depth. It encourages reasoned inference.
Makes sense. And they also use group normalization in this stage. What's that for?
That's applied to the advantage calculation, basically how much better or worse an action was than expected. It helps smooth out the training signal by removing noise caused by rounds just being intrinsically harder or easier for everyone.
So you don't get punished just because you happen to be in a really tough game round. It focuses on your relative performance.
Correct. It isolates the signal about whether the model's decision-making capability is improving.
Okay, so we have these two training modes. One optimizing clue generation, the self-play part. One optimizing spy detection, the ROVR part. But the real magic is how it switches between them, right?
Hmm.
This iterative SPO thing. How does it decide?
It monitors the performance of the civilians in the decision stage. Specifically, it tracks their average accuracy in picking the spy and how often they're saying nah.
So if accuracy gets really high, and they're rarely saying nah.
The system says, okay, the decision makers have gotten too good. This game is no longer challenging enough. And it switches the training focus back to the clue stage.
To make the spy better at deception. To generate subtler, more confusing clues.
Exactly. It ramps up the strategic difficulty. It forces the clue generators to improve their game, which in turn makes the decision task harder again.
And the opposite, if accuracy plummets or the civilians are constantly saying, I don't know.
Then the system flips back to focusing on the decision stage. The logic is, okay, the clues are too tough, or the visual differences are too hard to spot right now. Let's strengthen the decision maker's ability to reason and detect discrepancies before we make the clues harder again.
It's like a thermostat for difficulty. It keeps the challenge level in that sweet spot where learning is fastest.
That's a great analogy. It uses hysteresis, this dynamic switching based on performance thresholds, to avoid that plateau problem we talked about.
The game never gets stuck being too easy or too hard for too long.
And the ablation studies in the paper, they show this worked, right? Figure 7, I think. They compared iterative SPO to just training the decision stage, pure decision, or just the clue stage, pure clue. Yeah, the results were clear. The pure decision approach improved, but then flattened out. The pure clue self-play approach improved initially, but then actually degraded because the decision maker wasn't improving alongside it, so the reward signal became meaningless.
But iterative SPO, the alternating approach, showed sustained improvement. It kept climbing.
Exactly. It demonstrates that both phases and the dynamic switching between them are crucial for robust, continuous self-improvement.
Okay, so the engineering is solid. The concept works. Now the results. Did this zero-human self-playing system actually perform well on benchmarks?
Astonishingly well, actually. Looking at their main results, like in Figure 2 or Table 1, Vision Zero achieved state-of-the-art or comparable performance on several key benchmarks.
Better than methods that did use expensive human annotations.
In many cases, yes. Across tasks measuring reasoning, chart question answering, and general vision-centric understanding. It's genuinely impressive.
The part that really grabbed me was the generalization result. They took the model trained only on that synthetic C-Levar data, the colored shapes game.
Right, the Vision Zero Quinn 7b model trained on CLA.
And they tested it on math reasoning benchmarks. Standard stuff.
Yeah. And that model showed around a 3% improvement over the base Quinn 7b model on those math tasks. Now, 3% might not sound world-changing.
But compared to what?
Compared to other models that were explicitly fine-tuned using hundreds, sometimes thousands, of actual math problems with human-verified solutions.
Wait, seriously? Playing spy games with shapes taught the model math reasoning better than doing math problems did. How is that possible?
It suggests the core skills being honed in the Vision Zero game logical deduction, comparing evidence, spotting inconsistencies, strategic thinking, are actually fundamental reasoning primitives.
They're domain agnostic?
Highly likely, yes. It learned how to reason more effectively, and that skill transferred to a completely different domain, like mathematics, even without seeing explicit math training examples.
That's kind of profound. It implies there's a deeper structure to reasoning that the game taps into.
It seems that way, and this connects to another big win: mitigating negative transfer.
Yeah, the problem where training a model intensely on one thing makes it worse at other things.
Exactly. It's a common headache. You fine-tune a model on, say, complex math reasoning from a dataset like math, and its ability to understand visual charts might tank. They cited an example, Eureka Quen 7b, which dropped about 10% on chart QA after math training.
Which is a huge performance hit. You gain in one area, lose significantly in another. How did Vision Zero fare?
Much better. Take their model trained on the chart data using the Vision Zero game. Not only did it improve across all 4 chart and OCR benchmarks they tested,
As you'd hope.
but it also showed an average improvement of about 1% on general vision tasks, totally outside the chart domain.
So no negative transfer. It actually got slightly better everywhere else.
It seems so. The skills learned in the strategic chart game reinforced, rather than conflicted with, general visual understanding. It suggests the learning is more fundamental, less task-specific overfitting.
Incredible. So better performance, amazing generalization, mitigation of negative transfer, and all built on a system that costs peanuts to generate data for, compared to traditional methods.
That's the summary. It really does feel like a potential paradigm shift, moving away from the slow, expensive cycle of human annotation towards faster, scalable, automated self-improvement driven by compute.
Okay, let's wrap up this deep dive then. We've explored Vision Zero, a fascinating approach that uses a gamified, strategic self-play setup inspired by Who is the Spy to enable vision language models to train themselves without human supervision.
And the key innovation wasn't just the game, but the iterative SPO algorithm that dynamically switches training focus to keep the challenge level high and prevent learning from stalling out.
The results are pretty compelling. State-of-the-art performance, remarkable generalization from simple games to complex reasoning, and doing it all with dramatically lower data generation costs.
The core takeaway seems to be that forcing models into these complex, strategic, multi-agent interactions can unlock surprisingly general and robust reasoning capabilities.
Which leaves us with a really interesting thought to ponder, maybe for you listening. If a relatively simple social deduction game could enhance logical and even mathematical reasoning in these models, what other kinds of complex, maybe even social or strategic environments could we design? What other fundamental human-like competencies, planning, creativity, maybe even things like theory of mind, could we potentially unlock in AI, not by direct supervision, but by setting up the right kind of game?
That's definitely something to think about. Where else can strategic competition lead AI development? A fascinating question.
Absolutely. Well, that's all the time we have for this AI peer review. Join us next time as we tackle another cutting-edge development.